Hi, so you are watching this video to understand a little bit more about how to do SolidWorks stress analysis. Now, as a precursor to this video, I'm going to warn you that you will not be able to learn absolutely everything about stress analysis in one single video, especially when it comes to machine design. So, you are going to need to have a little bit more context than that. I would encourage you to look up some other examples of how to do it. I'm going to walk through the design portion of how to set it up, and I'm going to expect that if you have questions about setting up the way that your model needs to work and the stresses and all the different components for your stress analysis, you can find that information other places on the internet. So I'm going to kind of focus on the more unique content, which is doing the design work behind the stress analysis. So let's go ahead and get started in SolidWorks. Now, before you get started in doing anything SolidWorks related, the first step that you have to take is you're going to need to do a free body diagram for every one of your parts. So for the project that I gave you an auto hammer project. Now, typically the way that this would work is you would put a motor into your system. Your motor would apply some amount of energy through the rotation of the mechanism. That energy would be stored in rotating components and moving components. There would be velocities and accelerations in play. And then the hammer comes down and strikes with the energy that the motor has been putting into the system. And when it strikes, that energy that's kind of stored in the system is then transferred into the hammer. And then the motor, again, kind of refuels the system with potential and kinetic energy and prepares it for the next hammer strike. From that, what you would then find is you would find the amount of force that is actually being exerted from your system. And then you would take that force that's being exerted by the hammer, you would calculate it backward, all the way back to the initial portion of your motor. Now, to simplify that process a little bit, we're going to make a couple of assumptions. We didn't have enough time in this project to actually sit down and do the full kinematic and dynamic analysis that would give us the striking force of that hammer. So instead, we're just going to make an assumption. We're going to separate these two pieces. So for the first piece, you're doing a dynamic analysis where you're finding out the velocities of the components, and you're assuming that the hammer does not strike anything. That's component one. That's the dynamic analysis. And the second one is the stress analysis. This is where I gave you a value of 1,000 times the hammer head weight is going to be equal to the amount of force that gets back transmitted. So the way that you set up your analysis is you have to draw out your linkage, and you're going to draw a static force. And for this case, the worst case scenario happens when the system does not continue to move after the hammer impacts. If you don't have any of the forces consumed by accelerations, this is where you actually end up with a more severe loading condition. It's a more conservative estimate that the entire system seizes. So again, for the interest of time, we're going to be doing this type of calculation. So what you would do is you're going to start in a kinematic analysis to understand the motions of the machine. Excuse me. Apparently need to hydrate better. To understand the kinematics of the machine, you start at the motor. You calculate what the angular velocity is of the motor, which is given to you. You then take that motor speed, plug it into the next series of components, see how they move, see the velocity of those components, and then it transfers down the linkage from the motor all the way to the hammerhead. For the stress analysis, it starts at the hammerhead, which is where the actual force output occurs, and then it travels backward through the system all the way back to the motor. So the way that you have to do this is you assume your system is fixed at the time when your hammer strike occurs. You apply the force through your system at that hammer strike. You're going to have to orient all of your pieces to the correct position. Assume it is fixed, which means it's not moving. And then you apply the forces in a static equilibrium position such that you assume that the system is not accelerating. It is in static equilibrium with a constant force. Now, this is going to be, you're going to end up getting a von Mises stress value by doing SolidWorks stress analysis. The von Mises stress value can be plugged into a fatigue failure value. So basically, we're going to assume that the stress goes between 0 and the maximum von Mises stress for your fatigue cycling. So keep that in mind when you do your fatigue analysis for each of your parts. Okay, and yeah, so you'll have to draw how the forces travel through each of the linkages. This goes back to drawing in some of your statics experience in engineering statics and how you have linkages that carry forces. I would encourage you to come talk to me with your linkage force analysis if you have questions on that. Well, once you have finished that portion where you understand what the forces are acting on each of the components, then it's time to plug each component into your SolidWorks stress analysis. So that's what we're going to be starting at today. So now I'm going to have to draw up a part. I'm just going to open a part that I have existing. So I'll go back into my 4-bar linkage, and I'm going to grab my coupler I already have designed here. When I bring, I suppose I should probably let you see my screen. Yeah, I am amazing when it comes to YouTube video creation. That's a lie. I'm pretty good at doing the basics, but I really struggle when it comes to being a professional. It doesn't help that I'm doing everything off of a laptop and I don't have a dedicated system, and I mean, I could make a lot of excuses, but it's whatever. So here, this is the coupler that I had. The input linkage was right here, the output linkage was right here. Now in this case, there's only 2 joints. In a static analysis, in a 2-joint system, if you do your sum of the forces in the x and y directions and your sum of the moments, what you end up finding is that this force and this force have to be equal and opposite because there's only 2 connections. In order for it to be in static equilibrium, there can't be a moment because the simple pin connections that allow rotation cannot carry a moment themselves. So we can take this and we can say, all right, this is a very simple model. That's nice. What I'm actually going to do is I'm going to create a brand new part, and I'm going to simulate having 3 different forces on the same part, just to give a little bit more rigor to what it should look like. So we'll start with sketch. I'm just going to draw a basic box, front plane, hello box. Start the origin, start out like this. We'll do some smart dimensions. We'll make this be 15 inches long. Not 115, just 15. And we'll make this be 2 inches wide. It'll be chunky. I like chunky. We'll go ahead and draw in a center line here in the middle. Which apparently is not a center line. I will select this, control select the center point here, and then make them coincident. Come on. So that now this line is fixed too. I'm going to use that center line, and I'll draw 1 circle here, which will be horizontal with the center line of that. So select the center point here, zoom in, select center point there, set them at horizontal, escape, and then define the radius, or the diameter of this, which I'm just going to make it be 0.5. Half inch is pretty thick. And then we'll define distance from this line to this point. And since this is 12 inches long, we'll go ahead and set this at, that's 15 inches long. So we'll go ahead and set it at 7. Okay. Alright. And then I will have one circle going to be about right here. And then I'll have another circle over here. So this is, again, going to simulate a little more than just your average component. It's going to have 3 forces on it. These will not be. Actually, I'm going to mirror this one over. Mirror. I'd like to mirror you. There we go. And done. So that one will be fully defined. And then we just have to define this circle here. So select this point, control click this line. Oh, my bad. I meant the center line. So I will delete. Okay, the line didn't show up. So this is, make these be horizontal. Smart dimension. We'll make this also be 1/2 inch. And we'll set the distance here. And we'll say this is 1.5 inches. Okay, now I am working in the IPS, inch pounds second system, so every unit I'm going to have to use is going to have to be IPS. I'll exit out of the sketch, go back in here, boss extrude. We'll extrude this up about 1/4 inch. Really thick piece, but it's going to carry a lot of force, so got to make sure it's thick. So we'll take this component and we'll do a stress analysis on it. Okay, so the first thing you got to do is you got to go into your SolidWorks add-ons, and while we have been using SolidWorks simulation, we don't need that one, so I guess I can click out of it. I need as much memory as I can get because I'm trying to live stream this, so unloading that library helps. And then, piece that I want, no, I need the simulation. We were using SolidWorks Motion. What am I talking about? We still need that one. Okay, ayo. I believe this is a motion study. Okay, it's still loading. Oh no, we have to go into simulation tab, that's right. Oh, SolidWorks is going to make my computer die now. Back to model. So what we're going to do is a new study. I've got to name the study. We're going to have this be a static. This isn't a frequency one. Frequency one is something you can do when there's repeated loading. Yes, you can do that. We'll just do a static loading. We'll call it static 1. We're not doing thermal, buckling, or fatigue, or, well, I mean you could, but we're not doing that. We're just going to do a static analysis to find the von Mises stress. So just hit OK. Now we have a number of things that we have to do. First of all, in any analysis you have a driving force and you have boundary conditions. So here, when you have boundary conditions, these are things that cannot move. When you apply a boundary condition, you are assuming that there is something rigid that it is connected to. I'm going to go ahead and zoom into this axis. So first thing you do is you have to apply a material. I tend to assume that most of the materials I work with are really low grade of steel. You may find that you have a very high von Mises stress. You may need to change the material, but if you just pick like an alloy steel, that's fine. That's not going to change anything. You can pick SI 1020 cold drawn hot rolled steel. It's not going to change your von Mises stress dramatically. So I'm going to pick 1020 steel, hit apply, and close. Now if I find a very high von Mises stress, what I'll do is I'll just simply choose a higher grade of steel to see if I can't reduce the safety factor for this component. Okay, so I've got the material. It's picked, I believe, up here. I don't know why this is so small. Nope, down here it says that I've got my AISI 1020 steel selected. The fixtures this is where I can apply your fixed geometries. You can apply your roller slider, which elastic supports. These are different types of connections. External loads, these are the different loads that you can apply. Now, as I mentioned, you model from the end of the hammer moving backward to the motor. So in this one, if the right end of this component is the one that goes to say the hammer, and the left end of the component is the one that goes to, say, the 4-bar linkage that connects to my motor, then my load is going to be applied from the right end and my fixed end is going to be on the left. So you need to know how force is being transmitted through here, which end is kind of being loaded, and which one's more passive or just kind of be accepting that load. So what I'm going to do is I'm going to apply a force. Now a force has to act over an area, so when you apply a force, you've got to pick something to connect it to. Because it's going to be transferred through this hole I made specifically for it, I'm going to pick this hole, select it, pick a direction, and in that selected direction, I'm going to pick the y-axis. Oh no, that was wrong. Ooh, that was nice. Select a direction. I'm going to pick vertical along this line here, so kind of shows that it's there. Units, I'm going to change this to English IPS just because, again, that's the system units I've been using. And then I'm going to apply a load of, say, we wanted 1,000 times the head. I'm going to put 5,000 pounds. Okay. Hit enter. Oh, it does not allow me to go that high. Link value. Come on. Okay. I think that allowed me to do it. Yeah, and so there it is, 5,000 pounds along that edge, which I probably should have made it the face. And go ahead and delete the edge. Select the face itself. Oh no, like an idiot. That was the direction that it was pointing. So it's acting on this face, a uniform 5,000 pounds. Okay, so acting on face 1, force acts in this direction. I would need to draw a line on this item and then select that line if I didn't have an edge that I could use that shows me the direction. So here the direction is this way. You can flip the direction by hitting the reverse. So here, if I want it to be 5,000 pounds down, I can do that. But I want it to be 5,000 pounds up because that's coming straight out of my hammer. That's what goes into this thing. Okay. All right. So the rest of these, I've applied a force, I've applied a location, I've applied a face to give it to. I'll hit yes. So now I've got one load. Now what I got to do is I need to, well, I also have my connections. Here you can set connections between points. I'm going to encourage you not to use the connections. I would prefer that you use the fixtures just because it's going to make things a little bit simpler, so to speak. So here, a fixed geometry is going to be anywhere where you have a connection. For me, I use pretty much only pin connections. So my fixed geometry here is going to be this spot and this spot here. And we will go ahead and actually I'm going to separate them because I'm going to give them a different type. This one is a fixed geometry, but in advanced, let's see. Oh, I don't want a fixed geometry though. I want, I actually do want a pin. I think you can do a pin with just one. Yeah, so here we'll put a pin. We'll put a pin connection right here. I'm going to apply no rotational stiffness so it can rotate about this. I'm not giving it strength data because I'm assuming it's basically rigid. And yes, it does not have any amount of translation. It also does not have, it does allow for rotation, so it can twist a little bit about that joint, so that's okay. So we'll go ahead and hit OK there. Okay, you can't actually do that. That's what I thought. That's not how you set up a pin connection. Here you have to do it as, might be as a roller slider. Let's see if this is the right one. That's a sliding contact. So it can roll about that face, can spin about it, but otherwise it is okay. I think if I hit okay, that's just fine. We'll find out. Just playing around with different fixtures. The fixed hinges. That may be what I'm looking at, is a fixed hinge. Yeah, I'll change the other one. Add a definition. Fixed hinge, so it can rotate. It just isn't allowed to move. Okay, so now that I have this, I do need to go into the shell manager. What the shell manager does is it's going to break up this giant part into individual little tiny pieces and perform numerical calculations to figure out what the stresses are. So when I click on this, oh, it's not, that's not what I'm looking for. I think if I just hit run the study, oh, you gotta create the mesh first, I believe. So here, that's, you're establishing a mesh. I'm going to make the mesh, I'm going to click on this face and have it be that way. I'm okay with it being in the center. If you have too coarse of a mesh, your forces tend to be a lot higher. If you have too fine of a mesh, it tends to have a lot more deformation. Also tends to take a lot longer. You can establish some mesh parameters, such as would you like to have curved ones? Curved ones take longer. Standard mesh takes a lot less time. You can establish maximum widths. Similarly, down here, you can have a couple of different ways for how it calculates the stresses as they transmit through. I would just leave the status as it is. Hit OK. It'll take a little bit of time for it to mesh it. And you're going to see that geometry turns into a lot of triangles. If you feel like this is too rough of a mesh or too fine of a mesh, you can always go back in and change that mesh. But now that I have the mesh, I go to run the study, hit the run button. This is where a time-consuming process happens. Depending on the processing speed, you will notice that your computer may take some different times. Really depends on what you're working with. Now here it's graphing von Mises stress. That's what we want. We see a maximum value of 1.175 times 10 to the 9th newtons per meter squared, so that's pascals. And we're seeing it right here. Now, in our understanding, this is going to be your highest bending moment. It's about right here. So I'm not shocked by that. About 5,000 pounds times whatever this distance is. Yeah, that's going to be where our maximum bending moment is. So, yep. Then what we would say is our max von Mises value is going to be this stress right here occurring at that location. Take a screenshot of this, and this would show up in your paper for your analysis of this part. Now we would do a static analysis to find out how much force is being exerted here and in that one direction. We would then do the next part that's connected to this circle and this part that's connected to this circle. Unless this is like you don't really have to do a stress analysis on your ground piece, which is your frame. I'm not requiring that, but I do require it out of all of your linkages. So you would do your next piece here to find out where the force is going and how it looks. Okay, so that's the foundation of stress analysis in SolidWorks. You can find a lot of other videos online that probably do a little bit better job. I just wanted to give you a quick overview of what's expected of you.